Okay, welcome back. Let me pick up with what we were doing last time with Viennot shadows, and I think I'll start by just doing an example. Let's see. Okay, so I want to take, let's say pi is this example that I've been using, which is 4236 517, and we can quickly do Robinson-Shenstedt to this permutation. So if I just, okay, so I want to compute P of pi and Q of pi. Okay, so we've done this before, but we can do it again. So 4 comes in here, and I record a 1 in this box, and then 2 is going to come in and bump out the 4. Okay, so I get 4 comes down here, and I put a 2 there, and I add a 2 in this box. Okay, now 3 just gets added here, so I put a 3 here. 6 gets added here, so I put a 4 here. Okay, 5 bumps out the 6. So I put 5 here. 1 bumps out the 2, which bumps out the 4. 1, 2, 4. So I put a 6 here. And finally, 7 gets added here. So I put 7 here. Okay, so now I want to do this shadow thing that I was doing last time. So let me see. Let me do it here. Okay, so I'll draw this picture again, maybe with more space. Okay, so let me see if I can do 1. Okay, cool. So this is 1, 2, 3, 4, 5, 6, 7, and 2, 3, 4, 5, 6, 7. Okay, so I'm going to plot. I kind of don't like it. Whatever. Okay. So I'm going to plot my permutation, which will look like this. So I have 4, 2, 3, 6, 1, 5, 7. Okay. And I had this shadow construction thing where I imagine that there's sort of light that's emanating from this point and it creates these shadows. I realized this morning that like this is not actually how light works. That like you know, you shine a beam of light, it's only going to make a shadow like that. It's not really. But okay, we're supposed to pretend that like you get this kind of picture. Okay, so it should look like this. So this is sort of like the boundary of everything. Like this is all the stuff that is contained in shadows of these points, and this is down here like all the stuff that's not contained in those. And okay, so I'll explain what I'll explain the connection in a second, but let me just go through what I want to do here. So okay, did I pull up this right? Yeah. So the next thing I want to do is, right, I want to imagine that I've now deleted this purple zigzag thing, and now I'm left with these 4 points, and I want to do the same construction. So if I'm just left with those 4 points, I do the same thing, and I get this picture here. Okay, now I imagine I delete that, and I get these 3 points, and I do the same procedure, and I get this here. And finally, I just have this 1 point left, and I'm going to do the same thing, and I get just that little picture there, okay? And what I want to do is look at these rays that I have going out to the east, and I want to mark the y coordinates of those rays. So here the y coordinate is 1, the y coordinate here is 3, the y coordinate here is 5, and the y coordinate here is 7. And I also want to take the x coordinates of these rays that are coming up at the north. So here the x coordinate is 1, here the x coordinate is 3, here it's 4, and here it's 7, okay? And what you can notice is that 1, 3, 5, and 7 are these numbers, and 1, 3, 4, and 7 are these numbers. Okay, so now, so that's not an accident, that's going to be the, yeah.
Wait, is the dot at 6 supposed to be at height 1?
Oh, did I mess up? Is the dot at 6? Wait. Oh yes, yeah. Sorry, I don't know how I did that. Okay, wait. Let me. Should I just redraw the whole thing? Oh, I think. What did I do?
I think 5 and 6 are just switched.
5 and 6 are just switched. Okay. Great. Then that's not that bad. Okay, and then here, right, so it's supposed to be in position 5, I have a 5. Okay, thank you. Yeah. Great. Okay, so that is the picture I was supposed to have. But it ended up, okay, by accident I got the correct numbers on the side and at the top. Okay. But now, for the second step, I'm going to take these, these northeast points that I see along my zigzag, and I'm going to turn those into another set of points. This is kind of crazy, but it ends up being the thing that you do. So I'm going to take this northeast point along this zigzag, and then I keep going, I get this northeast point along this zigzag, and there's a northeast point on this zigzag here, okay? It's clear what I'm doing there? So now I have these 3 points, and I can do the same thing. I can say, okay, I have these 3 orange points, so I do this construction. And this, okay? And I can now look at the y coordinates of these rays on the east, which are 2 and 6. And up on the top, I get 2 and 5. And you can see 2 and 6 are these numbers, and 2 and 5 are these numbers. And then finally, there's one last step, which I just iterate this. I see, okay, now I have one northeast point on this zigzag. So maybe I'll color that blue. And so the last step is I just have this 1 point, and I do this, and this is 4 and 6, and you can see this is 4 and 6. So the crazy thing is that this is like a way of doing the Robinson-Shenstedt correspondence by drawing these shadow diagrams, and you don't have to do any bumping or anything, okay? So let me see how much of this I actually want to prove. Okay, maybe I'll state something. Okay, so here's the lemma. let the shadow diagram, so I'll call this the shadow, well, maybe I'll say, okay, let the first shadow diagram and by the first shadow diagram, I mean just the purple part that I drew at the beginning. So without the like second step and the third step, so just the purple part of this permutation pi, which is, let's say, x1 through xn, be okay, as before. So in the example, so suppose a vertical line, so we choose some vertical line given by the equation like x equals k. So k is some integer, and so this is just like the vertical coordinate, or the vertical line with the x coordinate k, intersects I of the shadow lines. Okay, the shadow lines are what I was calling the zigzags. So in this example, it's the purple ones. So it intersects I of these shadow lines, and let y sub j be the y coordinate of the lowest point of the intersection with the jth shadow line. Okay, then the first row of this tableau that I'll call PK. So PK is going to be the insertion tableau of this prefix of the first k things in pi. So I just take x1 through xk. I do insertion to create some partial tableau out of this, which is what I'm calling p sub k. And this is y1 through yi. Okay, so let me explain what I'm doing here with this picture, although maybe I'll redraw. Well, okay, maybe it's fine. You just ignore the orange stuff and the purple, or yeah, the orange and the blue stuff for now. Let's say I took like k equals 4. Okay, so if I take k equals 4 in this example, then I want to intersect, like I want to take the line, okay, you can't really see it. Okay. I want to take that vertical line with x coordinate 4, and I see that it intersects these, like the 3 purple shadow lines. So my y1 would be this y coordinate, which is 2. My y2 would be this second y coordinate, which is 3. And y3 would be this third y coordinate, which is 6. y3 is 6. Okay? And what we can check is that if we did insertion here, but we only did the first 4 steps, and so if I took like, if I did just the first 4 steps of the insertion process, I start by drawing a 4, and then the 2 bumps out the 4, so I get this picture, 2 with 4, and then the 3 comes here, and then the 6 comes here, and so this is like the tableau that I have after 4 steps, and you can see that the first row is 2, 3, and 6. Okay? So we can prove this. Okay, so we're gonna just induct on K. Okay, so okay, yeah, so we're gonna assume, well, yeah, okay, let's assume it works for K, and we'll prove it for K plus 1. So there are a couple cases. So first, if x sub k plus 1, so the next number that we're inserting, if this is bigger than y sub I, so y sub I being what we've assumed is like the last number in the first row of our tableau after k steps. So if this is true, then the box, okay, we have some box k plus 1, comma, x k plus 1 will start, or maybe not box, but like the point, okay, let's say the point, starts a new shadow line. Okay, so for example, if I did this, but let's say with k equals 3, so after 3 steps we had this picture, and then we said, okay, the next number is bigger than what we have here, so that means that we just added this 6 here, and in this picture, what that corresponds to is the fact that that this point up here is bigger than like this line segment that we were intersecting here, right? So it's saying that like because the 6 is higher up than this, it means that here we're starting this new shadow line. Okay. Okay, so in this case, so none of y1 through yi change, right? Basically, because we're not like y1 and y2 were 2 and 3 here, right? They were 2 and 3, and then we just kind of shifted over, and they didn't change. But now we have just this extra 6, and that corresponds to the fact that we didn't really change the tableau, except we just stuck on an extra 6 here. So, okay, so they didn't change, and we get y sub I plus 1 equals x sub k plus 1, this new number. Okay, and that's exactly what we would want if we want this to agree with insertion, because this is just saying we're sticking on this extra number. Okay, so this case is not too hard. So now, on the other hand, let's assume, assume that, let's say y1 is less than less than y j minus 1, less than x k plus 1, less than y j, less than less than y I. Okay, so what this should mean, if we're in this case, is that when we're trying to insert x k plus 1, it should come in and bump out the y sub j. Okay, so this might be like here if we took this same example, but now we take k to be 5. So we have this new number, 5, that we're trying to add in, but it's going to bump out the 6. And so what we'll get there is that this point k plus 1, comma x k plus 1 is added to the jth shadow line. Okay, so what happens here if we go from like k equals 4 to k equals 5, you can see that the point 5 gets stuck here. And so then it just gets added to this third shadow line. So I just added on to the shadow line that I was constructing there. And that is basically corresponding to the fact that the 5 is going to bump the 6. All right, so it's like we have this 6 here, but this, you can think of this kind of little line segment here as like saying that we have to bump the 6 with the 5. Okay? So let's see. Okay, so the lowest coordinate of the jth shadow line becomes this new number x of k plus 1. So this will be like our new y sub j, so we could call it like yj prime, and this will be x k plus 1. But all of the other y values just stay the same. Right, we didn't change any of these here. So we just changed, like here, like in this example, we changed y sub 3 from being 6 to being 5. Okay, so I guess this agrees with insertion. Okay, so this is supposed to give a sense of why this is giving us, well, at least why this is supposed to give us the p-tableau of RSK, or sorry, of Robinson-Chenstead, because you can kind of think about what we're doing at, yeah, maybe what I want to explain is like if I intersect the purple part, just the purple shadow lines, with some vertical line, like what are the possibilities? Well, okay, it should be that like if you intersect here, like at just a single point, that basically corresponded to like this number didn't move, this number didn't change in the insertion process. If you hit it at like a ray, like a vertical ray, like here, right? Like here my x equals 4 line is intersecting this with the vertical ray, that corresponds to a situation where we're just adding on a new number, on the first row, and then when you intersect with a line segment like this, so if I drew this vertical line and it intersected this purple part just in this line segment, that corresponds to a bumping situation. Okay. I mean, we could also maybe do a different, like if I looked at the second step, if I just did like the first step here, actually we could just go through it. We could just do the whole thing. I could say, okay, the first step is I draw the 4. I'm just constructing the p-tableau, and that corresponds to saying, okay, I hit a 4. Right, okay, so I hit this ray with the 4 dot there. And then if I go over to k equals 2, I intersect at this line segment where it goes from 2 to 4, so that tells me that the 4 is supposed to be bumped out by the 2. If I intersect here, this line, I get a ray, and this ray tells me that I'm supposed to add this new number 3, because this ray starts at the height 3. If I then go over here, okay, I intersect another ray which starts at height 6, so that tells me I'm supposed to add a 6 here. If I go over to k equals 5, I hit this line segment which goes from 5 to 6, so that tells me that the 5 is supposed to bump the 6. And then here, I have a line segment from 1 to 2, so that tells me the 1 is supposed to bump the 2. Okay, except right now I'm not saying anything about like the next step, but we know that this is supposed to happen. I'm just keeping track of the first row for now. But then, okay, finally here we intersect this ray starting at 7, so we get 7 there. Okay. And then I guess the point is you can sort of convince yourself, and maybe I won't go through all of the details, but it's also in the book, but like if you wanted to then iterate this process and say, okay, what happens in the second row and the third row and so on, well, that corresponds to this iterated process where we draw the orange dots and their shadow lines, and then for the next step we do the blue one, and so on. Okay. Yeah, so this then, oh, I guess I didn't explain the Q tableau part. Okay, where is the Q tableau part? Okay, yeah, so I've explained basically why like these numbers are giving you the P tableau. I want to explain the Q tableau part. So if we think about, okay, maybe I'll write this out. Okay, so the entry K is added to the recording tableau, which is the Q tableau. In cell 1, comma J, when xk is greater than every element in the first row of PK. So this is exactly, or PK minus 1, I should say. This is exactly when we intersect a ray with one of these vertical lines. But I mean, that's exactly, like, if you just think about what we did here, we added a 1 here exactly when, well, in the first step, because we hit this vertical ray with the 1 there. And then in step 3, we intersected this vertical ray, and that forced us to add that 3 there. So that's why we should have a 3 there. And then in the next, when we hit, I should be looking here. So yeah, this 1 corresponds to this first step, and then in the third step, we hit this ray. And then in the fourth step, we hit this ray, so that's why we should have a 4 there. And then in the 7th step, we hit this ray, which is why we should have a 7 there. So this is basically why we're getting the first row of the Q tableau coming from the purple numbers at the top. And then I guess you can, yeah, maybe I won't go through the details, but again, you can iterate this process and find that the next row of Q of pi is what you're going to get from the orange rays, and then the last row is what you get from this blue ray. Okay. So, okay, here's a nice corollary of this construction. Yeah, so this is theorem. due to Schützenberger. So yeah, I stated this last time, but for pi in Sn, P of pi inverse is the same as Q of pi. And Q of pi, or sorry, is the same as, yeah, is the same as Q of pi, and Q of pi inverse is the same as P of pi. So taking the inverse of the permutation corresponds to switching to P and Q. And like this is not at all obvious from the bumping definition of the Robinson-Shenstedt correspondence, like doing this weird procedure, because like the stuff that you're doing to construct P, you're doing this like insertion thing, and here you're just like sticking a box in at each step, and it's like very different things. It's not obvious why taking the inverse of the permutation should swap the roles of these things, but I think this is the formulation that Schützenberger used to prove it, so it's like actually complicated to prove it in this way. But then Viennot, okay, so maybe I should write down this name at least once. Viennot. He came up with this way of thinking about Robinson-Shenstedt, and from this perspective, it's much easier to see why this is true. Because if you think about like what is, I started by drawing these purple dots, which was just the plot of this permutation. What happens if I take the inverse of my permutation? Well, that just reflects the plot about this this line, right? Because I mean, it's like I'm taking the inverse of a function, and that's what you do when you take the inverse of a function. But like really, what I'm saying is, like here, well, like 4 maps to 6 in this permutation. So in the inverse permutation, 6 should map to 4. So this dot should get moved to this dot. So it's like I'm reflecting across the like y equals x line. Okay. So basically, when you take the inverse of the permutation, the plot just gets reflected through the line y equals x, and then this whole construction just gets reflected through y equals x. And so then what you're going to get is like the 1, 3, 5, 7 in purple here end up becoming the 1, 3, 5, 7 up top, and like everything just switches. Right? Okay, so this should be sort of clear. So this is clear. By Viennot's construction, since the plot of pi inverse is obtained from the plot of pi, by reflecting through the line y equals x. Okay? Okay. So I think the next thing I want to talk about is also something that Schützenberger did, and this is called jeu de Taquin. So let me. Okay, so this is. Jeu de Taquin. Okay, so what is this? This is French for game of teasing, and so the name comes from, if you know like the 15 puzzle, where you've got like 15 boxes sitting inside of a 4x4 grid, and you're supposed to slide them around, and you're supposed to, I guess the puzzle was originally like try to swap or try to get them like into the correct order, but this is impossible because like you start with something that's in the alternating group and you're only allowed to do even or even moves, or I don't know, something like that. Anyway, the point is like you have these boxes and you're sliding things around, and so this is similar where you're going to be sliding things around in boxes, and so that's where the name is coming from. Okay, so let's see. Okay, so first, okay, in order to do this, I need to define skew shapes. So if, let's say we have a Young diagram mu, so mu is some partition, but let's say that the Young diagram sits inside of a Young diagram lambda, so literally you just draw these and like mu sits inside of lambda, then, so like as Young diagrams, then the skew shape or skew diagram, which is denoted by lambda over mu, well, is the set of boxes in lambda, but not mu. It might make maybe in some sense more sense to like write this, because if you think of these as like sets of boxes, all I'm really doing is I'm taking the boxes in lambda and I'm deleting the ones from mu, but it's typically written with the slash going this way, so I'll do that. Okay, so as an example, oh, and I'll say, okay, a skew shape lambda over mu is called normal if it's just like a normal Young diagram that we've been considering, which is the case where mu is empty. Okay. So here's an example. Let's say lambda is 3, 3, 2, 1, and mu is 2, 1, 1. Okay, then lambda over mu, like this diagram, should be, okay, so I'll just draw 3, and then 3, and then 2, and then 1. But now I want to delete like 2, 1, 1, which would be this part here. So I'm deleting like these boxes. So I end up getting this. Okay, so this picture that I have left is my skew shape. Okay. Okay, so a lot of the definitions that we've talked about for like tableau and Young diagrams and all that stuff, it applies equally well for skew shapes. So I guess if I use a term that I've been using before for like normal shapes, but I'm applying it to a skew shape, it's just like the obvious definition. And in particular, there's like a row word for a tableau of a particular skew shape. So as an example, okay, like I could draw this same Young diagram and I could fill it with boxes, or with numbers, I mean. So something like this. I could fill it with like 1, 2, 3, 4, 5, and I could say, okay, what is the row word of this? Well, again, I just read the rows each from left to right, and I go from bottom to top. So if this is like my P, then my row word I sub P would be 3, and then 4, and then 1, 5, and then 2. Okay. Oh, and I guess one other thing. I'll just stick this here. So say two skew partial tableau. Okay, just meaning partial tableau but of skew shape are, let's call them, I don't know, P and P prime are Knuth equivalent. Oh, maybe I don't have room here. Okay, hold on. Knuth equivalent, we'll do this, denoted P Knuth equivalent to P prime. Okay, if their row words are Knuth equivalent as like strings of numbers, right? So we have a notion of Knuth equivalents for just strings of integers, and so we can talk about pi sub p being Knuth equivalent to pi sub p prime. Okay. One other thing I want to define, so the anti-diagonal strip associated with, okay, maybe I'll just, with pi some x1 through xn is the skew tableau with x sub I in cell n minus I plus 1, comma I for all I. Okay, so what this looks like, it's very simple. If I, so the anti-diagonal strip associated with, say, 3, 1, 4, 2 is, okay, I just draw these boxes filled with, so I put a 3 here, and then here I put a 4, and then here I put a 1, and here I put a 2. So it's just like this shape going up like that, but I want it to be so that the row word of this skew tableau is 3, 1, 4, 2. Right, so notice that the row word is exactly what I started with. Okay. Okay. Okay, so now I'm going to do Taquin, but instead of writing it out, let me just do an example. So let's say I have a tableau like this. So it's a skew tableau. is my skew shape. And let's say I filled it with 6, 8, 2, 4, 5, 9, 1, 3, 7. Okay. So what I can do is I can pick a cell which is what we were calling an inner corner of mu. So if you think of this as like lambda, and here I have like this mu that I've cut out, an inner corner of mu would be like one of these boxes here. Okay. So I want to pick one of those. Let's just say I pick this one, for example. I'm going to put a little dot there. And now the rule, so I just iterate this rule once I've put the dot there. When I have my dot, I look immediately to the right and immediately below it. So I look at these two numbers and I see which one is smaller. And whichever one is smaller, I'm going to slide into the dot. I'm just going to swap it with the dot. So this is supposed to remind you of like this, the 15 puzzle where you're sliding things around. So I'm going to, in this case, slot, so the 4 is less than 6, so I slide the 4 up here, and I move the dot down. So the dot is now there, and the 4 now moved up here. Okay, actually, maybe I should not erase. Maybe I should do it this way. So I start with this, and then, okay, this will be the process. Let me just rewrite this over here. Okay, so I still have like the 6, 8, 2, 4, 5, 9, 1, 3, 7. But now, okay, the dot is going to swap with the 4, so the 4 goes up. And now I have a dot here. Okay, now I do the same thing. The smaller of 5 and 7 is the 5, so the 5 will slide over into the dot position. And this turns into a dot. Okay, now finally I look at, well, 9 and empty. I sort of just ignore the empty and I say, well, or I guess you could also think of empty as like infinity or something. But the point is, if I only see the 9, then the 9 has to move. So I'm going to move the 9 over here. And now the dot has basically exited. It's like reached one of the inner corners of lambda, so now we're done. Okay, so that's one move of Schützenberger, which I'll call JDT. Okay. Let's see. So okay, maybe one way I could denote this, maybe or a better notation is if I call this cell C. Right, so let's say like here C would be like the 1,3 cell. So that's this. This is my C. Then I could say, okay, there's this map which I'll call JC. Yeah, so it's this map JC, and it sends this tableau to this tableau here. Except you kind of ignore the dot. Like just think of this as a tableau without the dot really. The dot is just there as like a, to remind you of something, or to remind you where you started, and then you can kind of ignore the dot in. Okay. So this is Schützenberger, and let me just mention. Okay. Yeah, you might wonder, like, why are we doing this? Let me just mention that you can also do the reverse. So, like, backward Schützenberger would be where I take something like, well, let me do another example. We could take this here. so maybe I have like 6. Let's just do the same thing. 6, 8, 2, 4, 5, 9, 1, 3, 7. And I could start with my dot here. And I could just do the reverse. When I do the reverse, I just say, now when I go, so now I look at the numbers that are to my north and west, so these two, and I pick out the bigger one of the two. So the bigger one here is the 7, so I slide the 7 over. Now I have my dot. And now the bigger one among 3 and 4 is the 4, so I move the 4 down here, and I have my dot. And now I only see the 2, there's nothing here, so I slide the 2 over. And now I'm done. Now the dot is just sitting there, okay? So that was a backward move, which, okay, I guess maybe I should have, let me do it this way. 2, okay, I have 2, 4, and 7, and there was the dot here, and then this I'll call J superscript C, and it'll be what I just wrote. So 6 and 8. Well, okay, yeah. 5, 9. 1, 3, 7. Okay, I have my dot, and then I'm going to slide it over with the 7. So 7 goes there, and then the 4 goes down. And then this dot moves with the 2. Okay, and then now I have a dot there. Okay. But I can kind of ignore the dots. And I guess in this case, C was this. This was my box, C. Okay? Any questions? Okay, so, oh yes?
Can we relate the two in any way?
Yeah, so they should be, they should be inverses in the sense that if I did Schützenberger here, like starting with this and I did the reverse process, I would move the 9 back, and then I would swap with this, sorry, am I doing this right? Okay, are they? Hold on, what am I saying? I feel like I did something. Did I do something wrong? Okay, so the 4 moves, and then I move with the 5, okay, and then the 9, so that's fine. But I should undo it when I go back. Why am I not undoing it? Okay, now I'm confused. Okay, if C is a cell for a forward slide on P, and the cell vacated by the slide is D, then a backward slide into D restores P. Oh, maybe I was supposed to do the other convention. No? What am I doing wrong? Seven should move over, but then with the 5. Oh. Hold on. I'm a little confused about why this example has a 6 above a 5. I'm wondering if that is not allowed and this might be a typo. Yeah, are these supposed to be standard, yeah, these are supposed to be standard skew tableau. And I think this example that it's giving is not standard. I think that's the issue. Okay, so yes, to fix this, I needed this to actually be standard. So this, let's swap these so that it works. So this should be a 5 and a 6. And then everything should be the same, except now this is, I'm swapping the 6 and the 5. Okay, and now I think, okay, here I want to do the same. Yeah, okay, great. So I think now it works. If I do this process, the 4 moves up, and then the 6 goes over, and then the 9 goes over, so I get this. If I started here and I went backward, the 9 would go over, and then the 6 would go over, and then the 4 would go down. So I'm just reversing my path. Okay. Yeah, but I guess crucially it has to be standard in order for this to work. Okay. Yeah. Any other questions? Okay. Great. So, okay, let me just define something. Okay, so a sequence of cells C1 through CL is a slide sequence for the tableau P if we can legally form the sequence, well, okay, P we'll call P0, and then P1, all the way to P sub L, where yeah, I guess I want to say P sub I is J C sub I of P sub I minus 1. Okay, do I have the indices right? I think so. So the point is that I just have a bunch of cells, and I start with P0, and I want to say, okay, I'm gonna do this je de Taquin with my dot starting in cell C1. And then after that, I'm going to do another je de Taquin with the cell starting in, or with the dot starting in cell C2, and then I'll do it all the way to CL. And like this is a slide sequence, if that actually makes sense. So like, yeah, you just need to choose a sequence of cells so that this actually makes sense. And then we'll say, okay, or, yeah, maybe I should say, or PI equals J sub CI of PI minus 1. So I'm allowed to do a sequence of slides of both of these kinds. So I choose a cell, I do this process, and then maybe I choose another cell, and it could be that like here I'm doing like the first kind of je de Taquin where things are going that way, and then maybe in the next step things are going this way, but you have some sequence of these. And then the point is that, okay, we have these moves, these je de Taquin moves, and we're going to say that some tableaux are equivalent. So say P and P prime are equivalent. Written P equivalent to P prime if P prime can be obtained from P by a sequence of slides. Taquin slides. Okay, so one thing we want to show, one reason we're doing this, we want to show that actually two skew tableaux are Knuth equivalent, which again means that their row words are Knuth equivalent, if and only if they're equivalent in this sense. Okay, so that's what we'll show. Okay, maybe I kind of want to skip over the proof of this, but I'll just write this proposition. So first, okay, so if P and P prime are standard skew tableau, then if they're equivalent in this sense, that implies that they're Knuth equivalent. So their row words are Knuth equivalent. Okay. So maybe I won't prove that. But what I can, okay, I'll just state another definition. So I'm going to let J of P be the normal tableau, or the tableau of normal shape so normal in that sense, so it's not like actually skew. So the tableau of normal shape obtained by doing jeu de Taquin repeatedly to P. Okay, so what I mean by this is, so I could do it with an example here. Let's say I take P to be something like what I had here. Okay, so maybe P is this thing. Okay, so 1, 3, and 7. And then 2, 4, 6, 9. And then here I have 5, 8. And what I'll do is, okay, I want to find what is J of this. Okay, so J of P will equal, okay, so I'm going to draw this again, and then I'll do a sequence of these jeu de Taquin things to turn it into a normal shape. 2, 4, 6, 9. 1 through 7. Okay, so I have some freedom. I could start by using this. Maybe I put something there. Okay, so I could do that. If I put my dot there, I'm gonna move the 1 up, and then the dot is here, and then it swaps with the 3. Now the dot is there, so it swaps with the 7. And now the dot escapes. Okay, so now I have this. And now, actually in this step I have no freedom, I have to use this one. But okay, it's gonna swap with the 4. Because the 4 goes up. Now my dot is there. It has to switch with the 6. And now it has to switch with the 9. So now I have this. Again, okay, now I have to put my dot there, and it's going to swap with the 2. Okay, now it's going to swap with the 6, and then the 9. Okay, and then finally I put my dot there. It's going to swap with the 1. And then it's going to swap with the 3. And then it's going to swap with the 7. And now we're done. Okay, so this is J of P. Okay? Yes?
Does it matter, like, the order in which?
Right, so it turns out that it doesn't matter. Was that also your question? Okay, yeah, so that's kind of interesting. And the reason it doesn't matter is because, let's say that I had 2 different, or okay, how do I want it? Yeah, okay, sorry, what is the reason for this? Yeah, okay, actually, I'll state this as a theorem. So, how do I want to say this? So J of P is the insertion tableau of the row word of P. Okay, so why is this true? So, okay, the reason is that, what am I missing here? Okay, so these, so P and J of P are related by a sequence of these moves. So if you believe this proposition, then they should be Knuth equivalent, which means that their row words are Knuth equivalent to each other. Now, the row word here, right, oh, so that means that they have the same, that their row words have the same insertion tableau. So the row word of P is the same as, or it has the same insertion tableau as the row word of J of P. So maybe I'll write that as, okay, so proof. Oh, yeah, I have this issue with the P's now. But, okay, so the insertion tableau, maybe I'll do like just for now, I'll do like a script P. So this is like the insertion tableau of the row word of P should be the same as the insertion tableau of the row word of J of P, because they're Knuth equivalent according to this. And Knuth equivalence is the same as P equivalence. Okay, so what that means is, well, the, okay, oh, I mean, yeah, so the insertion tableau for for this is just this itself. Because, yeah, so this is just a fact that we saw before, that the insertion tableau of the row word of this thing is just this. So that means that, like, whatever sequence I did, I ended up with some normal tableau, which had to be the insertion tableau of the row word of this thing, which means that it actually didn't matter the steps that I took. Yes.
Sorry. Are the two things not equivalent?
Which of these?
Yes.
Okay. They are, yeah, so they end up being equivalent. So, okay, maybe, yeah, for now, I was going to mention the other direction. Okay, I'll just do that. Yes, so they are equivalent. Yeah, so if you believe this, then this ends up being true. Okay. Right, so I guess so the reason for the reverse direction is that if they're Knuth equivalent, then their row words, yeah, so if they're Knuth equivalent, then the row words have to have the same P tableau, or the same insertion tableau. But then that means that you can do sequences of jeu de Taquin to get them into this normal shape, and the result has to be the same. And so that implies that actually they are equivalent in this sense, because you could just do the sequence that transforms you into the normal shape and then like undo the other sequence. Does that make sense? Right. Yeah. So again, I guess if P and P prime are Knuth equivalent, then according to this result, they have the same like J. Yeah, the J of P equals J of P prime, which means that you can just do the sequence of moves to get from P to J of P, and then you can undo this other sequence to go back to P prime. Okay, so then they're equivalent. Okay, so I think that's all for today. And next time, what do we do next time? Maybe evacuation or something. Okay, so yeah.